Okay, we're working on lesson 7, which is all about mental math. We're going to learn to perform arithmetic by using polynomial identities to describe numerical relationships. Okay, first thing I just want to sort of talk about. We're going to talk about performing arithmetic using polynomials. We're going to expand this into discovering whether or not numbers are prime or composite, which is actually tomorrow's lesson. So the first question, like multiplying 87 times 93, it's going to take just a bit of time. But the question is, can we use this form to make it easier? Okay, this leads into the difference of squares. Opening question, which is like our warm-up. How are these two equations related? I have this equation here and this equation here. Okay. Really, these are the same. It's the difference between multiplication and division, but we need to remember that x can't equal 1. We have the difference of squares identity. So explain the relationship between the polynomial identities x squared minus 1 equals x plus 1, x minus 1, and x squared minus a squared equals x minus a and x plus a. If this were a, a squared is still 1. So they're the exact same problems. Of course, we have a equals 1 here. A could also equal negative 1. So they're the same expression. So our first exercise, consider x plus 1, x minus 1 equals x squared minus 1. Okay, these are equivalent. If x were 100, what number sentence is represented by this identity? Which side of the equation is easier to compute? So if x were 100, we would get x minus 1, and x plus 1 is x squared minus 1. So it's much easier to compute 100 squared minus 1 than it is to compute 99 times 101. 100 squared, just make all your zeros. If I have 100 two times, I would have 4 zeros. Minus 1 is a lot easier. 1199. Okay, let's try that again with 95 and 105. That's really 100 minus 5, 100 plus 5. So our x squared is 100, and our b squared is 5. So it's a lot easier to compute. I have 4 zeros minus 25. Okay, this is our mental math exercise. And then this last one. 100 minus 7, 100 plus 7. 100 squared minus 7 squared, which is 10,000 minus 49, which is easy to compute. Thinking. So, did we notice any patterns? We saw the difference of two squares. So that's how we're going to use the difference of two squares to multiply any number. Determining the value of x and a can be pretty easy mentally, but we can also figure it out mathematically. We can look at the bigger number and realize if we subtract 8, it gets us to 100, which is what we're looking for. And if we add 8, we get 100, which is an easy number to work with. So it's the distance from 100 on the number line. Okay, so minus 8 plus 8. Pretty simple. That would give us, just to go ahead and finish the problem, 100 squared minus 8 squared, which is 10,000 minus 64, which equals 99. I need to get 6, which is 7, 36. How would you use the difference of two squares identity to multiply 87 and 93? What values should you select for x and a? How would you determine them? Okay, this one is not quite as simple, but still very possible. Because we can't use 100 with this one. But the two numbers are 3 above and 3 below 90. So 3 above would give me 90, and 3 below, made a mistake, would give me 90. So really, x is the mean, or, sorry, let me take off my watch, or the average, that's messy, of the factors. And a is, let's mean, half the absolute value of the difference. Between the factors. Okay, let's go ahead and finish this. This will give us 90 squared minus 3 squared, which is 8100 minus 3, 9. Ah! Which is 80, get the math right, 91. Okay, compute the following identities. So we said that our first term is the mean or average of the two factors. So 6 plus 8 is 14. 14 divided by 2 is 7. So I have 7. And then a is the half the absolute value of the difference between the factors. So 8 minus 6 is 2. So half of that is 1. So we're going to go 7 minus 1 squared and no squared. 7 minus 1, 7 plus 1 gives us 7 squared minus 1 squared, 49 minus 1, 48. Okay, add these two together, divide by 2. 19 and 11 is 20, 30, so 15 squared minus the difference between these two is 8. Divide by 2, 4 squared. 15 squared is one you should have memorized. 225 minus 16 is 209. Okay, why don't you guys try these? I'm going to push pause, just check your answers. And here you go. Push pause again and see if you got it right. Okay. Just talk about it. Which product is easier to compute using mental math? Explain your reasoning. I would say the difference of squares rather than multi-digit multiplication. Okay, next question. Can the product of any two positive integers be written as the difference of two squares? Okay, I don't know. Let's talk about it. If we look, we said that difference of two squares is finding the average or the mean of the factors and then the half of the difference. So what do we have here? Okay, for that one, I just quickly went through the numbers. It's just asking if you wanted to impress your friends with your mental math abilities and they gave you these three problems to choose from, which one did you pick and why? Oh, that's a typo, sorry. I honestly, I don't have 16 squared memorized, or definitely 45 squared memorized. I have 11 squared memorized, and it's easy to square that. So that one would be the one I picked, because I'd need a calculator to figure that one out. I might remember 16 times 16. Nope. No, 256. That one I definitely don't have memorized. So that's where the mental math is going to help, if the numbers are things that you know in your head. Okay, exercise 2. This one is sort of fun. Drawing a factor tree. We could just doodle. I could sit here and say, okay, if I have a number, two numbers multiply to make that number, and I can factor that even more, can factor that even more. I remember doodling when I first learned about factor trees. How many branches could I make on my paper? And then I would start again and see if I could make it prettier. Obviously, I'm not even making it green. And then I would get frustrated that I ran out of space. Like, wow. Factor trees, I've never actually liked them. Okay, in a factor tree, these are the vertices, and these are the branches. So, drawing a factor tree, the question we're asking is like, how many vertices do you see? Because those are all factors. It's really hard to count. So if we're doing factors of numbers, like even if we were squaring something, if we had 2, and we were squaring it, and then we were squaring that, and then we were squaring that, it's hard to count. Because factor trees are hard to draw. Not hard to draw, but you really have to plan out your space and make things neat and tidy. And if we looked, actually I'm going to go back. Now if I were to try to draw out a factor tree for this, sort of difficult on an iPad, but if I had 2 to the 0 power, that equals 1, so I have 1 vertex, and I split that up into, that would be the first level. Second level, I split that up into 2. Okay, we go down to the third level. I have 2 squared equals 4. Okay, fourth level. I have 2 to the third power equals 8. So I'm already frustrated because I can see I'm running out of space. Fifth level, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Goodness. This right here, that'd be the 30th level. How many, vertices would I have? That's a lot of tree branches. That's too hard to draw. Okay? How many vertices would a tree with 30 levels have? Okay, we can make an equation for it and use an identity that we learned a few days ago to actually solve it. So a tree with 30 levels, so that's the 29th. A tree with 30 levels is 2 to the 29. So 2 to the 29th actually equals that many vertices. And we can't count that. That's ridiculous. So how can we make it easier? So what we're doing here is we're actually talking about the identity x to the n minus a to the n. That was messy, which we learned a few days ago. It was the big ones, which would be x minus a, x to the n minus 1, a, x to the n minus 2, etc. And I'll get into that in a little bit. And we're going to talk a little bit about prime numbers. Prime numbers, what are they, first of all? It's a positive integer greater than 1 whose only positive integer factors are 1 in itself. Like 7. Factors are 1 times 7, and those are the only factors of 7 that you can get. A composite number can be written as the product of positive integers with at least one factor that is not 1 or itself. I don't know. Let's do 6. I've got 1 times 6 and 2 times 3. That's not a 3. That means it's composite because it can be written as the product of integers with at least one factor that is not 1 in itself. Got it. Okay, so let's write down the identity, which I wrote down here. Let's write down the identity x to the n minus a to the n. So that equals x minus a times, you can sketch this down if you don't remember it. All right, if we talk about is the number, let's say it's all right here, is the number b to the n minus a to the n prime. This is really what we're talking about today, or for the second half of the lesson. The first thing we need to realize, if b minus a is 1, then we don't know if b minus a is prime or composite. Because if it's 1, that means that our answer would be 1 times a number, which is prime, okay? So we're not sure. But if b minus a is greater than 1, then we know that it's not prime because we would have a number bigger than 1 times another factor. And it has to be bigger than 1. If it's 1, it could be prime. I sort of skipped something in the lesson. Oh, here we go. To make all of this make better sense, we know that if we had x to the n minus a to the n over x minus a, that would give us just this part of the identity. Okay, we did that in the previous lesson. We divided by x minus a. Now, if we use numbers here, so we have b to the n, let me make some more room here. We need numbers, not variables. B to the n minus a to the n over b minus a. B cannot be equal to a because then we'd be dividing by 0. But this is where I want to say all of this up here. If b minus a is 1, we actually don't know if it's prime or composite because we're dividing by 1. If b minus a is 1, then 1 is a factor, so it could be prime. It could be a different factor too, so it could be composite. So b minus a has to be greater than 1. Then we know it's not prime. So let's look at a real problem. 143. I remember that 12 squared is 144, minus 1 is 143. Okay, that's pretty simple. But if we use that identity that we've been talking about, where b equals 12 and a equals 1, we would do 12 minus 1 and, the rest of the math. And I actually don't have to do the second paragraph or second parentheses in the identity. Okay, we know that 12 minus 1 is 11, therefore 11 is a factor of 143. And therefore, that was a comma, not prime. Okay, we can I'm just going to double check, take my handy dandy calculator, goodness, and just do 143 divided by 11 and see what I get. So 11 times 13 is 143. And that right there is all that I needed to see if it's prime or not. Okay? Next question, is 2 to the 100th power minus 1 prime? Okay? We can try to apply the first identity. Let's see. So x to the n minus 1 will give us 2 minus 1. 2 to the 99 plus 2 to the 98th plus, holy cow. I don't really want to do that much math, so that's really awful. So let's try something else. Can I break this into a number that is somewhat easier to handle? Let's see. I know 4 times 25. This I can break into fives, which is going to be a lot easier to figure out. So 2 to the 4th. 4 times 25 is 100 minus 1. And that's going to get us 16 to the 25th power minus 1, which will give us that first parenthesis, 16 minus 1 times 16 to the 24th, etc. Okay, this right here is 15, and 15 is a factor of 200, or 2 to the 100th power minus 1. So if 15 is a factor, then we know it's not prime. Basically, we need this number to be greater than 1, like we talked about a few slides ago. Then we know it's not prime. Okay, you guys try these. Find 2 additional factors of 200, or 2 to the 100th power, and then show that 8 to the 3rd power minus 1 is divisible by 7. And use the identities we've discussed. See if you can figure out. I'll give you a clue. You need to break this number into something else. Like we did 2 to the 4th power times 20, or 2 to the 4th power to the 25th power. Try to find 2 more ways to do that. And go ahead and push pause. All right, there you go. Go ahead and push pause and look through the work. And let me know if you have any questions tomorrow. Okay, last slide. Based on the work in this lesson, students can convert differences of squares into products, and vice versa, using the difference of 2 squares identity. And then, using that identity, we just need to remember that x minus a can't equal 1, and n has to be bigger than 1. Then the numbers of the form x to the n minus a to the n are not prime, because that first term gives us a number greater than 1. Then we know it's composite. Good job today.